Hello everyone, I'm really excited to bring you this conversation with Alessandro Parente, a fantastic scientist, ERC winner, thought leader, and friend. We talk about his lifelong quest to better understand how complex chemistry happens within turbulent flows and how his group is applying some of the latest computational technologies to reduce the environmental impact of many industrial processes. Whether you're a computational researcher who wishes to make a real impact on the ever-important landscape of sustainability, or an industrial player that wants to meet a partner that can really master numerical simulation and machine learning, I strongly advise you to reach out to Alessandro. But for the moment, enjoy this conversation. Hi, Alessandro. Thank you so much for being here. You know, for somebody that has a CFD background like me, you have one of the coolest profiles out there. So you got a PhD from the University of Pisa, and then you moved to the von Karman Institute. That is an institute that surely needs no introduction for anybody that has any background in CFD, but for the others is one of the most famous centers for turbulence and fluid dynamics in Europe and maybe all around the world. And then you joined the Université Libre de Bruxelles, you became a professor there and won two ERC grants, very prestigious, a starter and one very recent one for your project Invent. And now you also serve as the Vice Dean for Energy Transition, Societal Impact and Industrial Relationships. So I have to ask you a very simple question. What's the secret behind such a wonderful career?
First of all, thank you for having me on the podcast. The only thing I can say is that I like what I do, and maybe that's the only secret. And yes, then I like to think that I had a series of great mentors, and also, you know, I was at the right place in the right moment, and I really exploited the opportunities that I had. And indeed, I really like what I do, and this makes the process easier, even though it's challenging. So our job is not. It's not a standard one in the sense that you really need to put a lot of energy to make things happen.
Yeah, indeed. And I have to say, I really like what you do in particular. I think you choose one of the most dauntingly beautiful domains that I could think of. In particular, if I look at fluid dynamics in general, I think fluid dynamics is probably one of the most beautiful and most challenging of the physics I personally can think of. And this is, to me, or that's how I explain it to myself, is because of two main things. One is that fluids have an inherent capability of making elusive structures that matter happen, but structures that are difficult to capture, but very important. And the other side is that fluid dynamics has an incredible ability to host other physics on the top of the fluid one that make this kind of other elusive structure happen. So for example, if you think about a very simple fluid, you think about water, right? A pool of water. By itself, without any other physics on top of it, if you make the pool of water big enough or fast enough, you already start seeing the merger of these elusive patterns that you kind of have to solve, but at the same time they're really difficult to capture. And this is, let's say, a romantic way to introduce the concept of turbulence, right? So yeah. the Reynolds numbers on velocity and dimension. And it's something that every time I think about it, is incredible. Like, you have dumb water just there, and you can just have to make the pool big enough, or you have to move it fast enough, and then this kind of chaotic patterns that yet determine how the overall structure will be there will appear. And on the other side, fluid dynamics is also extremely potent in hosting additional physics. So if you think about this pool of water and you just put a little bit of ununiform concentration of a salt, right? And you put an uneven heating, even gentle heating of the solution, then you get all this complex pattern of the current that move our oceans and are responsible for the creation of all these ecosystems. So in both cases, to me, this is extremely beautiful, and I understand why you're in love with that one, and I'm particularly in love. But also, that's why it's so hard, right? Because turbulence by itself, damn water that just is big enough, it's a really, really hard problem. And on the top of this one, you choose to add a physics that is also probably one of the more complex. We are talking about chemistry. You're talking about your research field that is mostly turbulent combustion, and I hardly can think about something more exciting but also more difficult. How did you come up to end up in this field? So how did you pick it up?
So I'm a chemical engineering by training, engineer by training. So I was trained in Pisa, as you said, and in Utah, and chemical engineers have this specificity that they can actually they deal with complex systems, multi species, and at the time where I was graduating, there was this. It's interesting because already at that time, so it's now more than 20 years ago, there was this interest in hydrogen. So it was hydrogen combustion as a way to decarbonize some sectors. And
big challenge of humanity that are not going to be solved in the next 1 year, right? Already when time ago, yeah.
Yeah, but I mean, there was the surge, let's say, of of the hydrogen way we live today, and it was very interesting because I mean, I rapidly got very excited about combustion. The complexity, as you were mentioning, of this process that adds up to the complexity of turbulence, the potential interactions between these two phenomena that actually lead to very complex kind of processes. And so I actually started looking into that, and then built my expertise step by step. And also in that, the path that I had was very helpful because I was in Pisa, a very good university, but maybe not the resources that I could find in the US. So I went to the US. I was exposed to HPC, so very powerful computers, and these codes.
And I guess it's another, let's say, complexity on top, right? So you have to make a code that can resolve this semi-chaotic, but still you have to be able to resolve it phenomenon of turbulence. You have your chemistry layer on top, and now you cannot run it on a local PC. You have to understand how to distribute the load of this solving these incredibly big matrices on connected machines. That's a nice beautiful story. Fractal way in which your relationship with the complexity expands. Yeah.
So that's a funny story. When I was in Utah, I was actually working on a project that we were solving a pool fire. So you will actually think to have a pool, not of water this time, but a pool of a flammable mixture. And then you would, the interest was to actually characterize from this pool fire, so the evaporation, the ignition, and the combustion of this pool, and let's say its relation to, and the relation of that with and the heat transfer of this process to, I don't know, a reservoir that could potentially contain flammable material, right? So I was working on that, and getting excited about this project, and so my supervisor there, Professor Phil Smith, actually gave me the task to manage what is called a dedicated allocation time, DAT, where you actually get the chance to run a full weekend on a big machine onto the computers of the national labs. And so I was all by myself running through the weekend simulations on 6,000, 10,000 processors. Huge.
Wow.
And but there is a catch. The catch is that since you're running on the entire government machine, if anything happens, they are allowed to call you whatever time of the day. And so I received the call at 3 a.m.
You get resources for computation, but then they can call you 2 a.m.
At 3 a.m. they called me to tell me that my simulation was actually was
crashing the government servers.
And so I had to wake up, log in the machines, check what they're going on. And then solve the issue, and then go to bed again. It was a nice experience too.
Yeah, and I think very relatable to a wider set of problems, right? This kind of energy that you put into going head first in this incredible amount of complexity, but also taking these kind of deals, right? So, okay, you kind of renounce your sleep, but then you can use very big machines. And I think to me, it really re-echoes with what I see today in the evolving fields of technology in general, right? So we are trying to tackle more and more complex things. We are somehow the same, let's say, brain capacity as before, but we have to deal with layered complexity, right? So to have this kind of know how to dance with turbulence. That's why I probably will call this conversation a chemistry with turbulence, to understand how to get something that cannot really entirely be solved, but say, I want to be the man that managed to solve enough of the problem to make a significant step, and then keep dancing with this with this complexity. And I see this definitely you master it already on the field of CFD. But I see this becoming more and more a reality also in the field of machine learning, when the models that used to be very simple are becoming exponentially more complicated. And it kind of, to me, re-echoes a little bit this aspect of turbulence, right? So this aspect of also when you solve a turbulent simulation, right? You have to deal with a computational engine that becomes very sophisticated, less explainable, and more difficult to handle. And I think that this is what is happening also on the machine learning field right now. I also had a very interesting conversation with you in the past about machine learning and the edge between CFD and simulation with machine learning. What's new in your agenda from that one? What's the most exciting field of machine learning for you from your
For
perspective
combustion,
right now?
for combustion, let's say in general, my prospect now on machine learning is so as you mentioned, machine learning combustion is very complex. It can interact different levels with turbulence. It can enhance turbulence. It can suppress turbulence. And when it comes to combustion, there are, in modeling combustion, there are many challenges. One is the fact that you introduce a lot of very small scales in the system, and so you have to resolve them. We're talking sometimes, of scales that are much smaller than the ones of turbulence. So you have to actually be able to solve them.
More or less,
And you
can
have,
you do you have numbers in mind about the length scale of a typical turbulent flow that you normally treat, and the, let's say, combustion scale?
so
Where
what I
does
mean
it
is
ends?
that sometimes you have flame layers that are actually smaller than the Kolmogorov scales. So it means that
Wow.
you need to solve properly a flame. You need to have enough grid points within the flame front, and so this can result in requirements that are twice, three times higher than a simple DNS for a fluid flow. Huh?
Wow.
Yeah,
Already DNS is like the I will never solve it for real,
that's
and now you get also smaller than that.
yeah. Then
And the scale, is there any kind of scale separation attempt? Like if I think about pure
yes.
turbulence and LES, right? These attempts to separate a little bit the scales, but just
Yes.
in a way in which are there similar techniques when we talk about turbulence and these?
Yeah, so there are several classes of methods that have been developed in our field where you look indeed at the relative scales of turbulence and chemistry, and you see whether chemistry can be decoupled. So there are some regimes where it's possible, some where it's less possible. In reality, you always have some kind of overlap, but you can actually get around this with the approaches, and this is also where machine learning is helping, in the sense that the other I was mentioning, so the scales, the fact that you have very many, in general, many species, chemical species. A large. So in fluid dynamics, you usually have transport of momentum, energy, and mass. On top of these equations, you have to count hundreds of equations more for chemistry, which means that the cost in terms of computational requirements becomes very very
Yeah,
demanding.
we have this ideal final metrics that which dimension that we are assembling, which dimension are kind of exploding. And then I think it's not just a single metrics inversion. In practice, you probably do that iteratively with smaller matrices, but kind of that's the concept, right? That's the problem. You're going this kind of huge monster that gets bigger and bigger. Yeah.
Exactly. And then you also have the problem of turbulence chemistry interaction. So where now combustion modelers with AI are working is really into reducing the number of species to transport. And this can be done with the dimensionality reduction, so unsupervised learning in AI. And it will also be done, there are also a lot of research in developing subclosures. So, models that can describe turbulence and turbulence chemistry interactions with machine learning approaches. And then there is an area, and this is where I really think there is a lot of potential, and personally where I'm working a lot, is the development of digital twins. So digital shadows, digital twins of complex, large combustion systems, because there is a lot of potential in really helping in the decarbonization process of large industries. So when you look at the hard-to-abate sector, so very easy to think about glass, steel, all these kind of sectors. You have the issue of having very big systems in very interconnected industries that will be important even in a net zero scenario. So you need to actually decarbonize them and taking decisions about, what happens to the process? What happens to my product if I use, starting from tomorrow, hydrogen or ammonia? These are fuels that we're talking about at this stage because they are carbon free. And so there is a need, I think, today of tools that can give you with confidence the way of exploring, scenarios such as the interaction of these fuels into very large combustion assets. And so for them, neither the experiments nor the simulations are today sufficient, because simulations can be, computationally inaffordable. Experiments do not give, in this kind of harsh environments are very, very difficult. So you really can leverage the power of AI, I think, in this field.
And as a follow-up, two questions that popped in my mind while you were telling this very comprehensive picture is in one of the challenges that I faced, in a couple of challenges that I faced, when trying to use traditional, let's say, PDE solvers or PDE's approach, let's say finite elements or volume approaches to solve a problem. Apart from this dimension that becomes very big, sometimes when you work with industry, you have the issue of the equation system is not really there, right? Especially this happens in chemistry very often, in which you have some description of your problem with some chemical reaction, but often chemistry gives you the main reaction that happened. But when you look at specifically, you are a company that is doing a specific sub process, and you are doing your own, let's say products that are not standard products. You actually don't have the kinetics of the reaction happens there. You cannot write them. So you have the problem of it will be too big anyway, but that's also something industries are looking at machine learning for. So even industries that normally rely on numerical simulation, because this kind of part of the problem of the physics is something they don't really have books of physics that tells them that's exactly what should happen, right? But on the other side, they have a lot of data because they kind of were producing whatever they are producing since ages, right? So they actually run experiment by themselves. And so this is kind of a potential of integration of the two, of getting something from the data and still having the equation. It's something that you see also in combustion, or combustion being so well studied, you kind of always are in the situation in which you know your chemistry well enough to potentially solve it, apart from, of course, how big this computation would be.
So I would say that in combustion we know pretty well chemistry. Of course, is not the case for all the fuels, and in particular now for many new molecules there are some uncertainties. For instance, we talk about ammonia. Ammonia is true; it is very well known for. It's something that we use in the agriculture since a long time. But for combustion, it's a kind of a new use, and so chemical kinetics mechanisms development started from the chemistry of selective non-catalytic reaction processes, so these processes to reduce NOx. But there are still pathways that are not known. And in fact, there is an emerging use of AI tools, and for instance, physics-based pins kind of approaches, where people really use the data to infer. At this stage, I would say to infer whether certain pathways are relevant or not. I think maybe the future will be to actually find new pathways.
Yeah, indeed, you talk about pins that I think for these kind of issues are a very interesting approach, because they live really a little bit into the middle between the typical equation-based and the database approach. And on one side, they, if you look at it from an equation perspective, so you're a FEM guy that wants to use pins, you kind of quick your eyes a little bit, because they will never really strictly enforce perfectly your equation like you could do in a mesh-based method or direct. At the same time, they don't give you the all problems that the fully data approach will give you. That is, if your problem dimensionality gets big enough, you need so much data that often is very expensive to gather, right? If you're talking, for example, about combustions, but I leave a little bit in between. So they are, to me at least, what I get on this one. We have a series with Enrico about this, in which I'll try also to learn more myself about pins. But they have this kind of middle player, right? So there's something that can give you a good first-hand approximation, right, and can allow you to ingest some data there, but then they will not be your full solution all the time, but they are a very good first-hand approach. I think. Have you used pins yourself already?
No, not yet. And we actually use other machine learning approaches, let's say, at the moment. But we are actually thinking to use pins in order to complement sparse experimental measurements. This is what we want to try to do. Of course, in that case, we should compare whether other approaches like regression methods based on radial basis functions could be easier for our purposes, because as you mentioned, we have sometimes to enforce constraints, and so
yeah, indeed. And kind of one of the things of pins is that they inform your overall method of the physics rather than enforce the physics. Let's say you could see it like this, and sometimes you really need the enforcement of, I don't know, mass conservation. In your case, not volume, because you're working with very compressible stuff, so probably volume is not really conservative in what you do, but at least mass conservation. And if that's a key point for you, then you know that a pin might risk to not really enforce it. Of course, maybe it's a big ecosystem, so I guess there are probably techniques to make them more enforcing, to have this kind of loss function related to the equation taking a bigger role, but still it's kind of within the technology, the fact that it's very good at informing. If you have a data set and you want to inform them of some physics you already know, that's kind of probably the tool to go with, but at enforcing, they are not really made for that, all right? Yeah. But you are not really stopping there, if I got it correctly. You have a lot more complicated and a lot more interesting things that are coming up into your future. Would you pick one for me? Just tell me, if I have to think of you, where will I see you working in the next years or years or so?
Yeah, so we're actually busy now on a series of projects which are interconnected, I would say. So we have I'm running a Marie Curie action. So we are actually coordinating these 10 PhD students. They work on hybrid physics-based machine learning methods for combustion modeling, and particularly, we focus on these new fuels, hydrogen, ammonia. We focus on new technologies that can deliver high efficiency, low emissions, and large fluid flexibility. And in this Marie Curie, we really look into the basics, how to develop new models, how to actually use to advance the field of physics-based machine learning methods. So, methods that can, as we discussed before, retain information about the physics of the process, not just interpolator or regressors. And so this means, for instance, having models that are still physics-based but can, improve or have correction or, be enhanced in a certain way by the knowledge of the data. This,
such an incredibly interesting field. I think that's the dream of everyone. Everybody that was only equation based always dreamed that of getting some of the data that will inform them of, okay, things are not going according to your model, right? And at the same time, database people that say, yeah, okay, but do I really have to teach a neural network, let's say, Navier-Stokes equations? We already have a way to solve them, right? So do I really have to show a neural network how water goes into a pipe? I already know that, right? That's
I
such an
think
incredibly
that's
cool
a
field.
nice combination of views. As you say, it's very different when you talk to really science, computer science people. They don't have the same view that we have. We have in terms of people that work with the equations, and I think there is a nice middle place there that should be explored, middle ground. This kind of approaches we're also exploring. In the Marie Curie, this is a very fundamental level, so we really work on the methods and so on. But then we also have projects at industrial scale, and so we are now working with the company. It's a European project, and we have as objective to actually decarbonize a real aluminium scrap recycling plant that has to convert their burners, the huge furnaces, into to the use of hydrogen. And so we really work with them into developing a digital twin for their furnace. And so this is actually a very nice combination, because we can bridge the scales from the very fundamental work up to developing a model for a real furnace. And I think this is a little bit the leitmotif or the common thread of this stage of research in machine learning. We have it's maybe also related to the specific time. We're living a time of big societal challenges. We have this climate change issue. We need to bring solutions. We have a knowledge of processes. So we have this knowledge that is actually booming up about machine learning, but we still have to solve some issues about its fundamentals. And so it's not very uncommon to see at the same time projects at TRL that are very, very different, I think.
Yeah, and it's, I think, what's your profile. I always admired a lot of your profile. That is, you know how to live in the both worlds. In the very theoretical one, getting very, very theoretical things out for Turbulence, but also in the very applied. You have a lot of tools at your belt, and you really like to go for applied problems as well. And so I think that everybody in the let's say university or academic field really already knows how to reach you. One question: if I would be a company and would like to have a talk to you about digital twin on all this incredible research you do, what's the best way to reach you?
LinkedIn.
LinkedIn, okay. You have also a very good profile and extremely interesting post coming up on that one. So that will be just your name and surname, Alessandro Parente, and they could have for sure extremely interesting conversation with you, like the one we are having today. So thank you again, Alessandro, for taking your time to talk to me about the crazily interesting things you're working on and the many things you're working on. And I hope we can have follow-ups to this conversation, because every time I talk to you, new ideas come in my mind, and I'm always amazed about how many groundbreaking things you're actually doing while keeping being super humble and super modest. So thanks a lot.
Thank you.
Thank
you very much, Gabriele.
So this was our first take on the beautiful world of turbulent chemistry. Let me know what you think about it and any theme you would like this channel to focus on next. We have our third episode on pins coming up soon, and I hope to see you there as well. Thank you so much for watching, and have a great day.